National 5, welcome back to the channel. Some of you are going into school this week, exciting times. But we're still got a couple of videos left to do, so my bad in kind of preempting the end of the videos. Note, we've got a couple more, but not to worry, I've got a special video just before Easter for all of you folk. Now, what I thought I would do today is play a little bit of chess, because I know some of the National 5s, especially in my class, love a bit of chess, so I would share some of my chess skills, or lack of chess skills for that matter, in the video. So I'm going to pop over to that in 3, 2, 1, let's go. Right, National 5, let's get into this. This guy is rated at 250, which if you don't know chess is incredibly low, so I'm going to beat him. I'm not great, but I'm going to beat him. It's just how quick am I going to do it. Now, I'm going to do so many mistakes here. I'm going to do a lot of mistakes in this game, okay, because I'm just going to do as fast as I possibly can. So we're going to see how long it takes me to beat him. Let's do this. Okay, let's just go straight off the bat. Okay, I can't do a 4-move checkmate anymore. Let's just keep going. Fast, fast, fast. Right, what's he done that for? Can't get that, can't get that. That's fine, we're just going to keep on going. Bring that gap there. That's fine, keep the pawns going. I'll break into that then, that's fine. Happy to do that. Okay, he's doing that odd. I'm just going to do that, why not? Well, he could have taken me with his queen, but he didn't do that because he's obviously not very good. So that's going to keep going. I'm just going to keep doing this. Actually, I'm going to bring that guy back over there. Do that. Fine. Here we go. Oh, he's not even moved his horse. Nightmare. Nightmare for this guy. Let's just see how quickly it can take to beat him. Let's just keep going with this. No, I'll support that guy up there. That's fine. So, bring that up there. Oh, what am I doing here? I am going to castle. There we go. Get that line attack there. Do that. Fine. Absolutely fine. Oh, he wants to attack my horse. What am I going to do? I'm going to just bring it up here. Perfect. Alright. This guy's kind of got... Oh, what has he done? Absolute nightmare. And he's not even got my horse. What is he doing? Oh, I could get my horse now. No, he's not. There we go. We're getting through it now. Let's just keep going. There we go. We are going to leave that guy there. We're going to do this. And then we're going to do... Okay, so let's see. Oh, I guess I've got that there. So do you know what? I could probably just keep doing that. And, oh, do you know what? Keep that guy there. So he stops hounding me. Get another queen. There we go. Bring my horse up, my castle I should say. Oh, what have I done? Well, he's not even got me. See, loads of mistakes here. This is why we're playing him. Right, let's keep going. Let's do that there. He's not got much, he's not really got many places to go, does he? Let's see, let's just bring this dude up here. We've got to try and play this right. Play this right. Okay, how are we going to do it? We're just going to bring this guy up here. And I think he's trying to go for the stalemate, but I don't think he's that good, so I don't think that's actually what he's going for. Do that. Put him in. I've got to be careful here. Got to be careful here. So I'm going to do that. And then I'm going to... I'm protected there, so I'm not protected there, so I'm going to do... I'm going to do that. And we're very close. We're so unbelievably close now. So here we go. That there. And that there. There we go. We've won. How long did that take? So I got 2 blunders, 1 mistakes. There you go. I said I was going to make mistakes. Didn't take too long in the end. And that is a victory for Mr. Bull. But I imagine many of you would be able to beat me in chess. I am not very good. But that was not too bad. Not too bad. Right, National 5, let's talk about space and all things space. I'm going to head over there in 3, 2, 1, and let's go. Alright, National 5, let's get stuck into this after a little chess game. Today we're going to be looking at space prelim revision. But first of all, like, share and subscribe. We're so close to 300. It'd be amazing if we could get 300 by the time we get back to Easter. That would be incredible. Anyway, we're looking at space. What is going to be in today's lesson? It's going to be on space terminology, rockets, which should be again a revision from the force topic, and challenges with space travel. Now, let's just rattle through some of this stuff. Space terminology. Before we do that, I always like to show some images from space, okay? So I'm not going to spend too much time because you've done all this before, and if you're in my class anyway. Pictures of black holes, okay? This is one of the famous new pictures that they took, basically one of the first pictures proving that the black holes do actually exist, rather than just seeing the effects of black holes. So that's been really cool. And this one here, deep field, image taken by the Hubble Space Telescope, where there's just an unbelievable amount of galaxies in this picture. And I just think it's one of the coolest space images out there. We have the Milky Way, taken from Earth, okay? If you have a long exposure camera, or you have a telescope with a MacBook, you could probably get a picture like that, but it does take a lot of money to get good quality photos for astronomy. And then obviously the pictures of spiral galaxies. I mean, some people might think that's the Milky Way, but we don't know what the Milky Way looks like because we are in the Milky Way, alright? So, just another spiral galaxy, and this was actually an image taken of I think the furthest away star that we've ever managed to view in a telescope. All right, and you can just see that in the bottom right corner there, just it kind of forming there. So yeah, really, really, really cool picture there. And the creation pillar, or the Eagle Nebula, this is basically all these wee pink stars are basically new stars, new birth stars starting fusion, and this cloud there is basically forming stars as we speak. All right, obviously over millions and millions and millions of years that will form. But yeah, another very cool physics image. And then we have the sun and some sunspots on the sun there. Obviously a solar filter is needed to even view the sun, otherwise we would damage our eyes. But that is all fun and games. If we were in class, we would obviously be chatting more about that. But let's just talk through a few things from space terminology. So, things you need to know. You need to know definitions of a planet, a dwarf planet, moon, and an exoplanet, which is just in this slide. So, again, I'll quickly go through it. A planet is an object that orbits a star. Dwarf planet is the same as a planet, but smaller. A moon is an object that orbits a planet. And an exoplanet is a planet that orbits a star outside our solar system and is so far away from Earth that we are unable to see it. Okay? And then the next ones we need to know are a star. A star is a ball of gases which produces heat and light by a process of nuclear fusion. We have done fusion and fission in the radiation topic, but this is nuclear fusion. An asteroid is an object that's even smaller than a dwarf planet. Galaxy is a system of hundreds of thousands of stars and dust that is both spinning and travelling. We've seen pictures already of that just moments ago. And the universe is the whole of space which can be detected. So, lots of stuff there. Primarily things like stars, moons and planets and exoplanets are the kind of highlighted ones there that I would be learning for your prelim. And obviously our sun is a star which gives off both heat and light, same as another star. Okay, we obviously have 8 planets. I'm not going to go through any of this because we know that stuff and it won't be asked in an exam. However, this will be asked in an exam. Light years. Light years are extremely important and something we need to know how to do. It is always based on distance speed time. Okay? If you're finding a light year, you're actually calculating the distance travelled by light in 1 year, and we call that a light year. Okay, so basically, to do this, we need to find out the speed of light, which we should know is 3 times 10 to the power of 8 meters per second. That's what you always find out when you're doing your first part of your S3 physics. And then we need to find out the time it takes in 1 year. Okay, so obviously the time of 1 year is 365.25, because remember that's actually the accurate level number of days, because we know that there's a leap year every 4 years because an extra day is added on from the 0.25. So we make it super accurate and say that there's 365.25 days, times that by 24 hours, times that by 60 minutes, times that by 60 seconds, and times it by however many years are in the question. Okay, sometimes it might be 4.3 years, or sometimes it might be 100 years, or whatever. Okay, 100 light years, I should say. So if we do that, looking at the screen there, we get 1 light year is 9.5 times 10 to the 15 meters. Okay, so lots of questions will ask you basically how to calculate a light year, and to do that, you will just have to use distance, speed, and time.
Okay, let's look at an example. The nearest star to our sun is Proxima Centauri, which is 4.24 light years away. Calculate the distance in between the two stars. It's just distance, speed, time. 3 times 10 to the power of 8, as we said, times 4.24 years, 365.25 days, 24 hours, 60 minutes, 60 seconds, gives us 4.01 times 10 to the 16 metres. There might be a question very similar to that in the quiz or Google form. Alright, super easy, nothing to worry about there. Right, rockets, moving on swiftly. Okay, so we've done a lot on rockets. Again, nice little pictures of rockets there, and the formatting issues have come once again. We know that there is Newton's third law affects rockets, okay? So every action has an equal opposite reaction. So if you have propellant gases pushing backwards, then the rocket ship should start moving forwards. All right, that is in Newton's third law. Okay, selfless plug. There's another video here, Mr. Bull's experiment. Check it out. Okay, it's basically me making a rocket out of vitamin D and water and seeing it explode. Bit of fun. Check it out on the YouTube channel. Okay, so we talked about Newton's third law. As I've said, we've talked about that. I'm not going to spend too much time on that. Now, engine thrust is basically the force that we would describe as a rocket moves upwards. Okay, and as soon as a rocket stops accelerating in space, obviously there's no friction in space, it will move at a constant speed. Okay, so once it stops accelerating, it will move at a constant speed. Okay, because of Newton's first law, that something will remain at rest or at a constant velocity unless acted on by an unbalanced force. Now, again, sorry for the formatting issues. When something is taking off, this is super important because it's always worth 4 marks in an exam. Basically, what you always have to do in these questions is minus the weight from the total force going upwards. So total force going upwards minus the weight gives you the unbalanced force. Okay? So as I said there, F unbalanced equals the engine thrust minus the weight. So therefore the acceleration is going to be the unbalanced force divided by mass, just simply doing F equals ma rearranged for acceleration. 4 marks, we've done questions on this before, just be very, very careful for me. Okay? So, example, a rocket has a mass of 2.2 times 10 to the 6 kilograms. The rocket is launched vertically from the surface of the Earth. The rocket motors exert a constant thrust of 3 times 10 to the 7 newtons. Draw a diagram of forces acting on the rocket. Okay? It's very simple. Engine thrust upwards, weight down the way. Do not complicate that. Very easy, very straightforward. 2 marks. Number 2, calculate the unbalanced force on the rocket at liftoff. So remember, unbalanced force is the total thrust minus the weight. So to do that, we do W equals mg. We got the mass of the rocket times gravity on Earth, which is 9.8. That gives us 2.156 times 10 to the 7 newtons. To find the unbalanced force, we just take away the force, the total force, minus the weight. Okay, so you can see that there gives us 8.44 times 10 to the 6 newtons. So hopefully that makes a little bit of sense there. So that was B. Okay, again, any one of these ones you need a bit more time on, just pause it and have a wee look over. C says calculate acceleration. Well, we just use the unbalanced force and we do F over m, and that gets us 3.8 meters per second squared. All right. And then D says explain what happens to the acceleration of the rocket as it rises. Well, what we can say is that the acceleration increases due to the reduction of mass from the fuel being used up. So as the rocket ship goes up, there are more fuels being used, it lays way, its mass is lost, so therefore, using the same equation, A equals F over m, should give you an increased acceleration. So, that is the rockets. Very straightforward, you've done a lot of that revision already on the forces topic. Number 3 though, challenges with space travel is particularly useful for things like knowledge of physics questions, and you will have to know how some of these work. So, problems with space travel. Again, I'm going to go quite fast through this. It's all in your notes for the space topic, and you should have that. Times and distances involved are huge. It would obviously take a very long time for us to go anywhere. We have seen that in, for example, the Mars missions. It takes ages, many years to even get from Earth to Mars and do everything correctly. Okay, so how about getting from here to another side of the universe? Unlikely, is to put it mildly. Other things, fuel will run out, okay? We need to think of things like ion drives. A good physics series I like is called The Expanse, and that has things like fusion reactor engines and lots of kind of science fiction, but more realistic science fiction, all right? Or Slingshot effects can also be used, but that needs very precise mathematics, and there's only certain windows in which you can do that. So you're not going to be able to use slingshot effect when you're in deep space and they've got no planets around. Okay. Solar cells could be used to maintain life support systems, but these will not work in deeper space because obviously it needs the sun for it to actually get any energy, and if it's not close enough to the sun, it will not get any energy. All right. There's also increased exposure to radiation outside the Earth's atmosphere. All right. There's no protection of the atmosphere to keep you safe from the radiation, so we need spacesuits to protect us. Pressure and temperature differentials. There's zero pressure in space and the temperature is only 3 Kelvin. So therefore, you need to be protected from both of those things. All right. Lots of things here that are very, very important. And then I guess if you're returning to Earth, there's going to be many risks in terms of traveling at high speeds. And if you travel at high speeds, this is a very classic question that gets asked. If you collide, the rocket ship collides with the air particles in the atmosphere, causing large frictional forces to be created, and then therefore the kinetic energy of the spacecraft turns into the heat that you experience as the ship comes through the atmosphere. Okay, so those are important questions there and answers. Friction between the air particles and the spacecraft turning kinetic energy into heat energy. We give you 2 marks and a question that involves that. I think there was one last week. Okay, so without special protection, this means that the spacecraft would combust. However, we've got very special materials. One is stainless steel, heat shield from the Apollo that we used, and another one was silica tiles to protect it from the heat. Okay, so lots of different ways as well to protect the spaceship from the heat. Now, that is us done. I've gone through that very, very quickly, but I'm just aware that I don't want to spend 20 minutes going through all this stuff when actually the questions on exams are fairly straightforward. All right, the hardest ones will be the force ones. There's none of those in the Google form today because you've done plenty of them over the last few weeks. But do have a look at the Google form and try your best with the questions and see how it goes. They're all on space this week. So well done, National 5. 2 more weeks left before the Easter holidays after this. And I hope you have a good week. See you later.